Okay, so I try to ask myself, do we move this to the advanced playlist or not? But I figured, though it is only tested at the A levels, I think it's still a quite a nice topic to learn and quite interesting. And since I think most of the math involved here is basic trigonometry, which we've seen in other areas, and some concepts of geometry and vectors, most of which we've covered, I decided to just continue collisions and keep them in core concepts as a continuation of the previous video. In this case, we will do collisions in 2 dimensions, right? So yes, all of the collisions we saw in the previous video were also on a 2-dimensional plane, but the line of the collision is just, single one, meaning any vector there would only have either the A component or the J component. But now we're going to make it a little more fun, and we're gonna start with the basics and build on it, right? So we'll start basics there, kind of work backwards. Hopefully the light gives you a view. So what do we do first? We just started there. We said, okay, here's a straight line. That was the direction in which something, let's say a particle came down, and this was the surface, made contact. Guess what happened? The particle, Newton's third law kicked in. The particle got a little knockback here, which was the impulse that, the reactive, which was the reaction, right? This was the reaction. The particle came in with a velocity u, and it went back with a velocity v, right? And that was the math, and we know the restitution here, we know that, v by u, life is good. We're going to take it one step now and see what happens, right? I will now say, hey, I'm going to tilt, if I can, there's days when spellings aren't right, there's days when the lines aren't right, but now what I'm going to do is I want this particle to come back down, but this time it's not coming in from there. It's coming in at an angle. That's the angle that it's coming in with. So that is u. That's the particle. Right? And this is never fun, but we will make it fun. Okay, a lot better now. We will draw a dotted line to demonstrate the normal. So remember what I said the last time when I talked about this, that's because the collision was normal, i.e. this is a right angle, this is a right angle because the reactionary force is always along the plane of that surface. So when we did friction, remember we did friction force was coefficient of friction times the normal force acting. So even though gravity brought something down at an angle, it was always the normal force to the plane. The reactive force is always normal. That does never change. So in this case, what's going to happen is my reactive force is normal to the plane. That's my impulse reaction, right? That's the way my velocity is coming in. I'm going to define this as an angle alpha. You know what? I should stay in line with the convention of some of the textbooks. So guess what? I will abide by the rules of the Cambridge textbook. That's my particle. I'm coming down there. That is the direction of velocity u, and that is alpha. Okay, I'm more behaved. What happens now? You get the little knock, and then where do we go? Let's see if we can capture it with another color. Beta and direction v. This equation is no longer v by u. This is wrong. And the reason why this does not hold is very important. Restitution is always along the line of the impulse, and therefore is always along the normal. Restitution and the effective restitution only applies along the normal, but it is basically along the reaction, and the reactive impulse is always normal to the surface. This is a very important fact. So if I had a sphere and a straight line and they were colliding, their collision is always based on the tangent of, so in this case, obviously, this would be the tangent to the sphere and this, and they would both be normal. But if it was not the case, and if this ball was moving at an angle, and it was this is its center, then if the contact point was somewhere here, then when this thing, let's say, came all the way there, before its center, let's say its center was somewhere here, and had its knock, the reactive impulse vector is along this line. It's not, even though the direction of motion was here, the impulse vector is here. It has to be normal to this surface all the time. And notice that this corner of the ball does not even make contact with this. It receives the impulse and it takes off from there itself. Right? When we do spheres, we'll get into it, a little bit of geometry effectively, that's all. But anyway, for now, we have a particle. We understand that restitution always in the direction of impulse. So that's what you need to remember. But since we learned our forces and we know everything about resolving forces, we are very, very happy to say that in this direction, what are the forces that apply? The force coming in can be resolved as a horizontal component and a vertical component. If we balance the point of equilibrium, you could say that u of cosine alpha should be equal to v of, because there is no restitution, right? So the components must be equal, cosine beta, two angles. But there is restitution here, so incoming u of, maybe the way to say it is, restitution is inbound with approach velocity u of sine alpha separation v of sine beta. How does that sound? Okay, so what can I write this as? So I could actually write two equations here, isn't it? I have one equation which is v is equal to, actually v sine beta is equal to e times u times sine alpha. And if I divide that by that equation, I could probably write v cosine beta, and here I would do u cosine beta. I'm getting somewhere because the u's can cancel out and the v cancels out here. So if you know the angle through which you're coming in, you know the angle through which the projection will happen outside. That's an interesting relationship. If I was coming in at 90 degrees here, straight line, this is tan 90 is infinity. Infinity times E is infinity because E is between 0 and 1. If it was 0, effectively you'd get 0, but then tan 0, that means there is no, it's not going out, just sticks to the wall. But if it was anything other than 0 times infinity, it would be infinity, which means beta is also 90, which means if you come down straight line, you're going up straight line. The moment you start changing, if this was 0 degrees coming in, well, really no restitution applies at 0 because along this line there is no force of impulse, so that is invalid. So this checks out pretty well. This checks out, right? So this is a very valuable idea to take home. Again, you can memorize it as a formula, or you can just have a fair understanding of what is going on here. So this is something that I think is useful to carry with you. Let me take this out and then see what else we can do here. So now let's just look at these two vectors. So U is a vector, right? U is a vector and V is a vector. So U becoming V is sort of, you're saying U is becoming V. It's almost like identifying, if I had a vector U and then it's becoming a vector V somewhere, what is the angle of these vectors? It's almost like saying this vector is getting deflected into another, it's like it's coming in, it's getting deflected. And this angle is really alpha plus beta. And some people say theta and they call it the angle of deflection, the angle of deflection. And usually the reason why they call it so is like it's because they want to it's basically the vector angle of the it's the angle of the two vectors. So better if I did it on a coordinate system and I said if I came in with a u vector and if this is u vector and if this was v vector, then it's this angle is alpha plus beta. Now you can understand this by saying, if I knew my vector, if I go back to the concept of vectors, imagine if I was taking v and resolving it into the direction of u, what would I get? A quick addendum on the quick lesson on vectors. So I have these two vectors, and instead of coming this way, just move them, displace the vector. Is theta dot product multiplication. I just want to quickly go over that. So that's u dot product v. It's simply equal to the magnitude of one vector, right, times the magnitude of the other vector cosine theta, if you remember that. Because what I'm doing here is I'm taking this, remember, I'm bringing it here, and I told you that's what I'm doing there is taking the direction is already addressed here, right? So that value, and then if I did this math, I would just basically get cosine theta is nothing but the dot product of my vectors divided by their magnitude. So just an easy way to remember this. So just keep that in mind. But fundamentally know that this is like, maybe geometrically as well, we can show it, right? So if we draw parallel lines, and I draw that, and I draw another parallel line there, if this is beta, this is alpha, this is nothing but 180 minus alpha plus beta, right? If you're with me. But we know if two lines are parallel and there's a line intersecting this, then this is also the same 180 minus alpha. So you can actually, if this is 180 minus alpha plus beta, and this is the parallel vector, so this is the u, this is the u vector, and this is the actually, if I call it this way, u vector, and this is the v vector, this angle is nothing but alpha plus beta, right? So it's how much this is getting turned by. So this was the original u vector, and this is the original. So I might draw it in white here. The original u vector is here. That's the u vector. That's the original v vector. Now I have drawn a green color. Actually, maybe take this out. A green color v vector as a parallel, right? Just to show you the indicative signs. And this is the tail, just to show you what deflection really means. Coming in and the vector is getting deflected. Don't confuse it with this angle of deflection. That's not the angle of deflection. It's the vector getting deflected, right? So that's why theta is alpha plus beta and not that angle. And that's why the equation for them is through the resolved components of the vectors. So angle of deflection, another very interesting concept. Hopefully you understand that. Final idea for this section is what we talked about earlier. And if you have a sphere, I'm going to draw a big sphere here, so it is clear. The center of the sphere is here, and if it makes an impact straight line, this is I. But if it's an oblique impact, if the sphere came in from here, whatever is the direction of the sphere, center, that's what matters. Any force that comes in on a sphere, any directional vector, so its movement, its velocity, always gets mapped to the center of that sphere. And that is the line along which you apply that force. However, reaction vector always is normal to surface. Apply this, stretch this one step forward, take this out, okay? So reaction vector is okay. Reaction vector is here. The ball comes out this way. It's going to go back like this, even though the impact is here. So neither this part of the ball nor that part of the ball got any effect from the surface. The reaction vector is here, but the restitution is along this angle always, right? This concept, when taken, extended to two spheres, should be even clearer. I have another sphere here. If these two spheres collide along this path, this is exactly like doing collisions in one dimension. They come in collision in one dimension. Because the line of centers, which is this line, and I'm going to draw this in green, this is the line of centers, is along or parallel to the line of collision. Collision and impact are happening along the same line. Impact reactions, they're all happening here. Life is really easy when this happens. But the reality is, sometimes this is not what happens. What might be happening is, this is the point of impact, but this guy and this guy, they were moving in different directions. Let's say this one was coming in this direction, and this guy was going in this direction. Now you have an interesting case. So that was his direction of motion, and that was his direction of motion. Where does the map happen? Remember, impact is always normal to the line of centers, always along the line of centers. Why? Because calculation is a tangential plane, normal is a line of centers, okay? So that's where impact happens. Now the fun begins, right? Now the fun begins. Obviously, if these were equal radius, and this was exactly 90 degrees, the radius was equal, you'd almost certainly, you'd be able to, geometrically say 90 degrees, and this is 2r. You could always resolve because it's equal sides. everything would be fine. You could use plain geometry to come up with all the angles, but if they were not of equal radius, then immediately the geometry changes. But this line, fundamentally, if you can draw this line and work your geometry out, then you are fine. All your other calculations work against this, right? So now here you would say, this is the impact vector, and here this would be the impact vector. And this is the reactive impacts. One going this way and one this way. So what would restitution look like? And what would the reflection look like? So if this guy is coming here and he's getting impacted this way, but he's got, or let's say one of them was fixed and he's getting a, if the knock is here, then the reactive knock should send in that direction, isn't it? Because relative to this angle, he's coming in here. So this, maybe the way to do it is the color, right? So if this guy is fixed, let's just assume he's fixed. I'm going to move, right? And let's just say this ball is coming in and we're just going to use green, right, to demonstrate what's going to happen. So the impact is like that, right? He's going to come in here and he's going to either move this away. Obviously, there will be a change, and then this will go. So he will come in like this and drift away, and these would be the alpha and the beta that you can calculate. And the way you do it would be, and this would be the plane against impact, right? This would be, and I impacting I would be there, and the forces would be resolved in that direction. I'll take this arrow out, right? So the white arrows would obviously then, you would now draw the white arrows to show what happens to this guy. So this is all the green arrows to show what happens to the green ball. Now the white arrows show what happened to the white ball coming in here and going out there with its alpha here and beta here. Wow, I hope this is not too messy, but if it is, you'll have to excuse that. And I hope you get the picture. And this is the eye. So the white arrows show what happens to this ball in white, and the green arrows show what happened to the green ball. There we go. Just complete this so you have a here. So all this is the green ball. Right? You don't need that line for sure. Don't need any of these little annoying white lines. Let me just take all of them out. As clear as I can make it. So there you have it, right? So that is your collision, right? Original directions, let's say, were, in this case, that was the direction, and in this case, the direction came in here. So let's say this was there, so maybe this was the original direction, right? The line of centers is here. It's called the line of centers. As it says, it's a line that connects. This is the line of centers. This is direction of motion of, or I would actually say velocity of the white ball. And this direction is the velocity of the green ball. And you can see what happens. Basically, all of the mathematics that we did remain unchanged, right? So the angles of deflection, using the cosine relationship and sine relationship, you can basically calculate everything else. So hopefully this is fun. So a lot of math. It's a lot of fun. I mean, not a lot of math. It's pretty straightforward. But hopefully, you can work out the sine, cosine, and the tangent, and you can see how geometry helps you to see that the angle of deflection is really a deflection of the vectors, And you can also find out that it's as simple as doing a scalar. If you have a scalar dot product of the vectors, you have the answer, right? So that hopefully gives you a little more about oblique, the word oblique collisions. They're not normal for an angular oblique. And yeah, good luck with some practice problems. And I think at this point, I might start looking at some problems in this area as well. So until